me yesterday, too. Okay. All right. So let me start with a brief reminder of what we were discussing yesterday. So yesterday we had an overview lecture where we were discussing the main goals of string theory. So yesterday we're discussing the main goals of string theory. One of the goals is, of course, to unify all 5 interactions that we know in nature. So one of the goals is to unify all 5 interactions known in nature. Then we followed closely an analogy to Maxwell's theory. We know that Maxwell's theory was the first theory where we found a unification of the electric and magnetic force. And many things in string theory will be rather analogous to what we saw in Maxwell's theory. So we introduced Maxwell's theory of electromagnetism. And several things in string theory will be analog to this, to the electromagnetic interaction. So, like, for example, the electric-magnetic duality, the Dirac quantization condition, or electric-magnetic duality that we discussed yesterday. So the electric-magnetic duality. What we saw yesterday is that Maxwell's theory can be quantized, which means we can go ahead and compute Feynman diagrams of this theory. And what we see is that the predictions in electromagnetism are in good analogy with what we see from theory in experiment are in very good agreement. So Maxwell's theory can be quantized, so which is known as QED, quantum electrodynamics. And as I said, we have good agreement between theory and experiment. However, we saw that we are running into trouble when we try to quantize, do the similar thing in a theory of gravity, because our quantum field theory, let me call it a quantum field theory of gravity, is not normalizable. Which means that if we, for example, try to compute diagrams like this, where we have got 4 massive particles, and we call them M1, M2, M3, and M4, that interact through the exchange of gravitons. So these particles here are gravitons. What we see is that the coupling constant in gravity is a coupling constant that depends on the energy. So it's a coupling constant that is dimensionful. So kappa squared, what we saw is that Gn multiplied by E squared is the effective coupling constant. And the higher the energy of these particles that we have got here, the more divergent the diagrams will be. The higher the diagrams, the more interaction vertices we have, the higher the divergence will be of these diagrams, which means the theory is non-normalizable. So what string theory then does is to remove, so basically the problem is this point-like interactions. And what we saw is, if we look back in history, we saw that a similar phenomenon occurred in the early days of the weak interaction, where we had the Fermi theory of the weak interaction, which was based, again, on an interaction of 4 fermions that meet at a point. So the way to remove this divergences appearing in this non-normalizable theory was to smooth out the interactions. So string theory does the similar thing. String theory just replaces this point-like diagram that we've got there by a diagram like this, where we no longer have point-like interactions, so we have got a closed string. And what we see is if we calculate in string theory the analog diagram like this, so this is divergent. In field theory, however, this is not divergent, so ultraviolet finite, or ultraviolet means for high energies. In string theory, so let me define ultraviolet. Ultraviolet means for high energies. So what we basically saw is that there are two types of strings. We can have closed and open strings. And string theory basically rejects the idea that elementary particles are point-like objects. We have got finite, so point-like objects are no longer, elementary particles are no longer point-like objects. But different vibrational modes of a string. And what we can have is closed and open strings. So we can have either a string that is open, so something like this. So this is an open string. So this would represent one type of elementary particle. Then we can have something like this, or something simpler like this. No, this is the same thing. So let's leave it at this. So we can have an open string like this, or we can have a closed string, which is a string where both ends are identified. And again, different vibrational modes of a string. Each of these vibrational modes will represent a different, so this is a closed string, will represent a different elementary particles. And what we saw yesterday, more or less intuitively, we will see this today in more accurate formulas, because we will hopefully be able to compute the spectrum of the bosonic string, which is the simplest string theory that we can have. It's a string theory that is not very realistic because it contains particles that have a negative mass square. It doesn't contain all the elementary particles that we see in nature, but it's the simplest theory, and it illustrates the basic principles of string theory. So are there any questions regarding the lecture of yesterday? Okay, so then let me start with the lecture of today, which is, let me continue where I left off yesterday, which is the following. So one question you may want to ask, oops, this is difficult, is, so what is the size? Before I start discussing the bosonic string, let me finish where I left yesterday, is what is the size of a string? And the answer to this is rather simple. The size of a string is a very small object that can be, the size of a string can be determined by basically dimensional analysis, because it's of the size of the Planck length. And I tell you in a moment why you can determine this by dimensional analysis, which is around 10 to the minus 33 centimeters. And you can determine this by dimensional analysis, so which is very small. follows from dimensional analysis because of the following. So what we would like to have is, first of all, a theory that is a quantum theory, which means it contains an H bar. We would like to have a theory that describes gravity, which means it has to contain Newton's constant. We would like to have a theory that is relativistic, which means that it has to contain the speed of light. And if you make this combination here, put the power to the 3/2, we would have the dimension of a length. And this quantity here, if you plug in the numerical values, is of the order of 10 to the minus 33 centimeters. Which means that to an external observer, a string will effectively appear as a point-like object, which explains why string theory at low energies, or why low-energy physics has been so successful. The standard model of elementary particles has been so successful so far if you restrict yourself to very low energies. However, you will have problems if you go to very high energies. So what type of elementary particles do we have in nature, and what type of string theories do we actually see? So my next question we would like to ask is, so you may have heard this from your lectures on phenomenology, is what type of elementary particles do we have to obtain the string theory? So you may know this already. You know that in nature there are two types of elementary particles that we observe. So we've got nature here. We've got two types of elementary particles. First of all, we have got bosons, which have integer spin. Which are the particles that are the particles that are the exchange particles for the interactions, like the graviton that we saw. If you have got two massive particles, they interact through the exchange of a graviton. So the graviton would be one of those particles. It's a spin-2 object. We saw that the weak interaction has got particles interact weakly through the exchange of W bosons and Z bosons. So there are three types of bosons, B plus, V minus, and Z0. We know that the electromagnetic interaction contains the photon, which would be another one of these bosons that I'm introducing here. And, of course, you've got the gluons, which are the exchange particles of Q, CD. So then we have got particles that have half-integer spin, which are the fermions. Oh. So which are the particles that basically are the constituents of nature? The constituents of nature, and we know that there are two types of fermions. First of all, we've got the leptons, like the neutrinos. We've got the electrons. We've got the muons, or we've got the tau particle, and the corresponding neutrinos, of course. And we've got the baryons and mesons that are built of quarks. So string theory basically has two, and if I compute the spectrum that follows from a string, basically I have to be able to obtain all the sorts of elementary particles if string theory should describe nature. Theories that contain both bosons and fermions are so-called supersymmetric theories. So supersymmetric theories contain bosons and fermions. And supersymmetry is a very beautiful symmetry which you will learn from Professor Gates. Yes?
I'm okay with the formula you put up for the flame.
Can you repeat the question?
I have okay with the formula you put.
You would like to see the Planck of it. Okay, maybe I should, instead of pulling on this blackboards here, yeah, I should. So. It's 3/2, yes. Is it a half? Make dimensional analysis. So, okay. So check this. I didn't check the dimensional analysis. Either it's 3/2, so replace it. So question mark, homework, exercise, replace it's 3/2 or it's 1/2, just do dimensional analysis. So you know this is our speed, you know the dimensions of this quantity here, and you know the dimensions of the of h bar. So make dimensional analysis and see what you get in order to get a length. Either it's 3/2 or it's 1/2. I didn't do the calculation. So let me go further, and where I was discussing a moment ago. So I said supersymmetric theories contain bosons and fermions. So we're interested in principle in superstring theories. And in principle, people until 1985 thought, well, there are 5 different types. There was the so-called first superstring revolution, and people thought there were 5 different types of supersymmetric string theories. So the first superstring revolution, so let me call this first superstring revolution. Which took place in 1985, led people to think that there are 5 different types of supersymmetric string theories. Let me call them superstring theories. Which they call type 1. Maybe we should see later on what the specific properties of each theory are. Type 2b, type 2a, heterotic SO32, and heterotic E8 cross E8. In the so-called second superstring revolution, when people understood better non-perturbative effects in string theory and the duality, the electric-magnetic duality that we saw in Maxwell's theory, but now in the context of string theory, people realized that these 5 different theories are actually just one, can be derived from just one single theory that has been called M theory. So the second superstring revolution which was around 1995, people realized by understanding non-perturbative effects, or duality symmetries, led people to conclude that there are 5 different theories can be derived from one theory, from one single theory. That people called M theory. So we'll probably see more about M theory in the last lecture of this course. So which is very satisfying, because if you would like to have one theory of nature, it's not very satisfying to have 5 different types of string theories, it's very natural to have just one single theory from which you can describe all different types of elementary particles and not just having to decide which theory you would like to have. So, and it is our hope that in the next couple of years, supersymmetry, so it would be strong evidence for string theory that supersymmetry would be discovered in particle accelerators like the LHC or the Tevatron, which will be built, the LHC in 2005 at CERN. So if people would find their supersymmetry, it would be a strong indication, a strong point in favor of string theory, because string theory requires supersymmetry for its consistency. Yes?
Well, if they don't find the supersymmetric particle, does it mean the symmetry is broken more than expected, or does it mean string theory doesn't work?
Which it could mean, for example, that you have to go to higher energies. It would be rather disappointing if they wouldn't find it. But it could mean that you have to go to even higher energies to find supersymmetry. So, but people are very hopeful that supersymmetry will be discovered.
Is there any way that supersymmetry could be disproved easily?
Disproved? I don't think so. I don't think so, because it's a very beautiful symmetry that you need in order to explain the symmetry that you have got fermions and bosons that exist in nature. So it's a rather natural symmetry that you need. So I don't think that you would like to discard it. And also, one very nice thing about supersymmetric theories is that if you would actually like to do calculations are usually very easy in supersymmetric theories, or much easier than if you're dealing just in theories that are bosonic theories. So the idea is then to say, okay, my world is supersymmetric at very, very high energies, but at low energies, then supersymmetry gets broken. So you can do your calculations at high energies, and then you just need to understand how supersymmetry is broken, because supersymmetry would, in principle, predict that bosons and fermions, for example, have the same masses, which is not the case. So supersymmetry has to be broken in our world, but at very high energies, you have to have supersymmetry. Well, it would be nice to have supersymmetry, let me say it that way. So you wouldn't like to discard it. So it would be nice to just have it there. So one important, yes? Yes. Yes. You have to talk a little louder.
I'm talking about the experiment.
Yes. Yes.
From 2005.
Yes.
What do you think they discovered? Because this was talking about the technology is too far into the future to be able to discover strings.
Oh, they are looking for supersymmetric particles.
What are these particles?
Well, this is a guess. So the lightest supersymmetric particle is called the LSP, which is the abbreviation for lightest supersymmetric particle. So the question is, what is this? It's a particle that is stable. Question is, maybe it's the supersymmetric partner of the neutrino, which is called the neutralino. So what told us that? It's a guess. It's a guess. So people still don't know that, but this is what they are looking for. So it's a particle that is stable, so would make sense to look for particles that are stable, that don't decay so fastly that you cannot observe them in the particle accelerator. Okay, so what this would mean, discovering supersymmetry, would mean finding lots and lots and lots and lots of new particles. Each particle that we know in nature, where we right now are at not supersymmetric level, we would have a supersymmetric partner, so to say. So we would discover a lot of new particles. And our hope is that we will find them.
This is a very long way of energy. You see this underlying string structure, which is that's the energy scale.
Yeah, absolutely, yeah. But as I said, John Schwartz used to say that finding supersymmetry is more important for us than finding life on Mars. So That's one of the quotes that John Schwartz always says. So, as you see, for string theory, supersymmetry, finding supersymmetry would be very, very important. So, and the reasons why supersymmetry, so for a string theory, supersymmetry is very important. Because of the following. First of all, because a bosonic theory, like we will discuss a little bit later today, contains tachyons. The bosonic string contains tachyons. Which is a particle that has a mass that when I squared is negative, which doesn't make sense. It's an imaginary mass. So the tachyon can be eliminated in a supersymmetric theory. Another important feature of superstring theories, and which is the next subject that I would like to discuss, is that superstring theories only make sense if they live in 10 space-time dimensions. So we will see that when we compute the specific spectrum. So an important feature is that superstring theories have the rather peculiar property that they live in 10 space-time dimensions. As otherwise, if you compute the spectrum of this superstring theory, it will contain ghosts. Ghosts are particles that have a negative norm square. So otherwise, the spectrum contains particles ghosts which are particles that have a negative norm square. So it's like the harmonic oscillator. If you compute the norm of a state, you would get a norm that when you square it is negative. It's a ghost, which doesn't make sense. And you can eliminate the ghost if you define your superstring theory in 10 space-time dimensions. So the question is how we don't live in 10 space-time dimensions, we live in 4 space-time dimensions. How can we describe the world in 4 dimensions in which we live? And the idea is to do something that is called Kaluza-Klein compactification. I don't know what the best way is to use these blackboards here, because if I pull this up, let me just always follow one way, because otherwise it just disappears. So how do we describe? So the question is how we describe our 4-dimensional world? The idea is to do something that is called Kaluza-Klein compactification. Which is a very old idea. Which dates back, I think, to 1919, when Klein wrote a letter to Einstein, as I will mention in a moment. So let me illustrate for you what Kaluza-Klein compactification means first in the simplest example, where we just have one particle that propagates in one dimension, that is a compact dimension. Then we will have a particle that propagates in 5 dimensions, where one of the dimensions is compact and the other ones are infinitely extended. And string theory is basically a generalization of what we're going to discuss right now. So let me mention the first simplest example, and let me start there again, because otherwise So let's consider a particle to illustrate the idea of what Klein compactification means. Let's illustrate the idea, the simplest example. So consider the simplest example. Consider a scalar moving in one dimension. Take a scalar moving on a circle. I will need this as an ingredient to explain the more complicated case later on. So if the scalar is moving on a circle, let me take the coordinate on the circle. So let me define x, the coordinate on the circle. And since we are defining a circle, what we would like to do is to identify x should be identified with x plus 2 pi r where r is the radius of the circle. Okay? So if we have got a field phi, so let me take a field phi of x that propagates on the circle, that moves, let me say it in that way, field that moves on the circle. Then, of course, this field should satisfy that phi of x has to be equal to phi of x plus 2 pi r. Because what we would like is always each time we have a line differs by a factor of 2 pi r, would like just to identify. So if I've got somebody standing here, we will always identify events that differ by a factor of 2 pi r. Okay? So what we can do, if the field satisfies a condition like this, what we can do is to expand this field in periodic eigenfunctions. So phi of x can then be expanded in periodic eigenfunctions. And what we can write is that phi of x, you will see in a moment why this is so important when we go to higher dimensions. Phi of x is equal to the sum from minus infinity to plus infinity, some coefficients that I will call phi n e to the I pi x, where if I would like to satisfy the condition that we have got this periodicity condition here, that phi of x is equal to phi of x plus 2 pi r. What we see from here is just by inserting here, replace x by x plus 2 pi r. what we see is that the momentum pi has to be quantized. So momentum pi has to be quantized. In units of n over r. So pi is equal to n over r, where n, let me lift this a little bit, is an arbitrary integer. Okay? So why is this important for us? So let us have a look at how this generalizes, if we would like to consider the propagation of a particle in 5 space-time dimensions where one of the dimensions is, 4 dimensions are infinitely extended, and one of the dimensions is very small and curled up. So it's like with this little slinkies that we've got here. So if you've got a big slinky here, you will see here that it's you will see that it's an object that has got the dimension of a circle. If it gets smaller, you will see it's almost one-dimensional. So if you got even smaller like this, you will see a dimension like this. And if you go even smaller, you will just have a stick here. So you will be dealing, where do I have my stick? So you will be dealing essentially then with a one-dimensional extended object instead of having an object that is extended here that has a length. And a two-dimensional, you will be seeing just a one-dimensional extended object. So the basic idea is that to see our world, one of the dimensions is so small, it's of the order of Planck length, that we cannot see it, and we just see the infinitely extended number of dimensions. So let us illustrate this idea by considering the idea that we have got a particle moving in 5 dimensions. Where one of the dimensions is very small and curled up, while the other 4 are infinitely extended. So the question is, what happens in this case? So let me call the dimension that is very small, x5. So let me introduce the following notation, x0, x mu. Let me call this for where mu runs from 1, 2, 3, 1, 0, 1, 2, and 3. Let me call this the infinitely extended dimensions. And let me call x5 the dimension that is compact, which is the analog of what we saw a moment ago for the particle moving on a circle. Which means that x5 again satisfies x5 is equal to x5 plus 2 pi r. So what we would like to do is to consider the propagation of a massless particle. So our goal is to consider, let me write down over there maybe, erase this. So our goal is to consider the propagation of a massless particle in 5 dimensions on a space that has a form like this. Question is, what do we see? And what we will see is the following. So you know a massless particle satisfies the equation dm, so the equation of motion. For a massless particle, you know that you have got an equation of motion, dm acting on phi. Let me call the 5 coordinates x equal to 0, where m runs over the 5 coordinates. Okay? All right. So what we will do is, again, to do the same thing that we did for the one-dimensional case. We can expand this field in periodic eigenfunctions. We can expand the field phi of x in periodic eigenfunctions. And we know again that we have to satisfy the condition that phi of x5 has to be equal to, because this is the compact coordinate, it has to be phi of x5 has to be equal to phi of x5 plus 2 pi r. So we can satisfy a condition like this if we expand phi of x in periodic eigenfunctions. So x denotes all the 5 coordinates that we have. So x, let me introduce the notation. X are the coordinates on the 5-dimensional space. So we can write phi of x in the following way. Phi of x is equal to phi of x mu, x5, which is equal to the sum from minus infinity to plus infinity, phi n. But now this phi n will depend on the 4-dimensional coordinates x mu multiplied by e to the I, the momentum in the 5 direction multiplied by x5. And again, in order to satisfy the condition, that we have got a periodicity like this, the momentum in the 5 direction has to be quantized. So let me call the star to satisfy star. We again have to have that P5 is equal to n over r where n is an integer. So what do we see? If we apply to this field x5 now the 5-dimensional equation that we saw a moment ago, so the 5-dimensional massless Klein-Gordon equation. So what we see is the following. So the massless Klein-Gordon equation, 5D massless Klein-Gordon equation, will tell us, you just do the calculation. Where do I have my eraser? You just do the calculations. You insert the expansion of your field. So you consider here this index m running over the 4-dimensional coordinates mu and the 5-dimensional coordinate x5, and insert your expansion that I've got right now here. So let me write better here. The expansion, okay.
4 dimensions.
Yes?
Or instead of the particle only allowed to move in the 5th dimension?
The The particle is moving in all 5 dimensions. Why is there no x mu in the exponent? Wait a moment. Oh, right, because this dimension is the periodic dimension. Yes, he's absolutely right. This dimension is the periodic dimension, and what I would like to have is that in order to satisfy this boundary condition here, I've got the x mu dependence sitting in the function phi n of x mu here. So this is the periodic dimension, and what I would like to satisfy is a condition like this. So I need to have an expansion like this one here. Thanks for asking. Any more questions? All right, so what happens if I now go ahead and apply my 5-dimensional Klein-Gordon equation to this field that I've got over there? So what I see is that I get the following equation. I get an equation that tells me d mu phi n of x mu is equal to n square over r square multiplied by phi n of x mu. So what we see from here, remember this mu were the 4-dimensional indices. This part here comes when I take the derivative of the field with respect to the coordinate x5. So what we see is that from the 4-dimensional point of view, this particle here is no longer a massless particle, but it is a massive particle which has a mass given by n square over r square. Yes?
Sorry to interrupt. I was thinking this might be a nice exercise for some of the students to actually show them.
Yeah.
And the reason it would be a nice exercise is because many of the students are perhaps not so familiar with the index summation notation that you're using.
Absolutely.
So
yes.
The process of going from dm on the board all the way to the left,
okay.
expanding that out, really realizing what every term.
Yes.
So perhaps you just
yes.
remind people
Thank you, Clifford. Yes.
what index notation means, and then they'll see where that comes from by playing it.
Absolutely. Okay, so exercise, please check. That from 1, you obtain 2, where 2 means this equation here, and 1 means this equation here. And let me tell you by using 3. So these are the 3 ingredients that you need. Oh, the only thing that this means is when I write down something like this. So a reminder, when I write down something like this, d mu, what it actually means is that I'm summing, so I'm considering d0 plus d1 plus d2 plus d3. So this is basically what the index notation means. Oh, okay. D mu means d by dx mu. Okay? Thank you. Excuse me?
What is, if that's a subscript version, what's the superscript?
You just raise and lower indices with a metric. So you just take x mu is equal to g mu nu. No. Let me just see if I get it in the right way. So you just raise and lower indices with taking the 4-dimensional metric.
Oh, okay.
Yeah? Okay.
The TV there.
Oh, yeah. Thank you.
It usually upstairs on the X in the definition of the derivative.
Oh, okay.
And also, perhaps, sorry to do this, if you remind what the metric is here, there's a crucial minus sign.
Oh, the metric. Okay, so what we have got, I'm using a notation where the metric, so G mu, so if I will be using later on, I will be using Minkowski space, so my notation will be eta mu is equal to, I think I'm using the conventions. You're asking about the conventions, right? So this will be the convention that I will be using for my metric.
Very first line. On the top, the mu in the phi is not to be contracted with the mu on the delta.
Oh, okay. All right. I think they wouldn't contract it. Okay. So, and as I said, what we conclude from here is that from the four-dimensional point of view, so let me finish the last remark that I was making above there, is that from the four-dimensional point of view, we see a particle which has a mass square, massive particle.
Just to sort of touch base with sort of more familiar notation, could you write out d mu in the sort of dt squared plus del squared notation?
Oh, well, the only difference is use d0. You can define as x0 as your t coordinate if you would like to. And you can define the other coordinates x1, x2, and x3. No, x1, x2, x3 as your space-like coordinates. So that's the only difference. Use one of the coordinates, x0, as time coordinate t. Does this clarify? Okay. So as I was saying a moment ago, so take this remark for a moment away. So as I was saying, from the four-dimensional point of view, what we see is a massive particle with mass squared. Which is rather interesting. And something similar will happen in string theory where we consider the Higher generalization of this picture. But before we go to string theory where we would like to consider the Higher generalization of a picture like this, so let me just show you one. How does this turn on? Oh, well let me leave it for... Okay, so basically what we do, we have to just plug it in. So what we basically do is in string theory to consider the higher generalization of this picture, where what you have got is our, where's my pointer? The pointer is gone, right? Oh, it's there. So what we have got is basically our four-dimensional, thank you, Clifford. We have got our four-dimensional world that is infinitely extended, which is what you see here. And at each point in space, it doesn't have to be a sphere. It's just a sphere for simplicity. You have got 6 dimensions that are very, very small and are curled up, and are sitting on each point in your space-time. So you won't be able to see this 6-dimensional internal space, which has got the size of the Planck length. So it's so small that you don't see it, and you only see the infinite number of extended four-dimensional dimensions. And the crucial point is that, as we saw in this five-dimensional example, is that the properties of the world that we see in 4 dimensions depend on the internal space. So, for example, what we see here is that the masses of the particles that we see in 4 dimensions depend on the radius of the internal space. So, in a very similar way, we will see later on in string theory, when we consider the higher dimensional generalization, is that the spectrum of elementary particles that we see in 4 dimensions depend on the properties, on the topological properties of the internal 6-dimensional space. Before we consider the generalization, the higher order generalization to string theory, let me apply this Kaluza-Klein idea to something that was used by Kaluza to unify, in the 19th century, to unify the theory of electromagnetism with the theory of general relativity. So there's a very beautiful way of doing this, and let me apply this instead, as I was doing a moment ago. Apply this calculation to the case where, instead of having a scalar, what we have got is a metric. Of course.
From that mass formula, how we hide that extra dimension, the way how we
it's a very small.
Yeah.
Well, the basic idea is that the radius is so small that we don't. At this moment, I have no way of fixing the value of the radius. But the basic, so that's one. Again, you're asking one of the questions that is rather crucial, and it's one of the recent developments in string theory, actually to be able to determine the size and the shape of the internal manifold. So at this moment, I'm not able to tell you the radius has to be big, it has to be small. I'm assuming that the radius is so small that you cannot determine this. But basically, from string theory, what you would like to do is to determine the value of the radius.
I was asking a simpler question. Just given that formula,
yes,
in this nice example, we can see that when R is very small, the particles that come from that hidden dimension become very heavy.
Very heavy.
So it's hard to, those are the only effects
yes.
of that hidden dimension.
Absolutely.
And so the smaller that dimension is,
yes.
the more energy you have to do to excite the particles because their masses are very heavy. So that's operationally how you see that the dimension is hidden. Let's imagine we lived in a 5-dimensional universe, and one of the directions was a circle.
Yes.
How would we see that? We would look for those particles.
Yes.
And we would have to build, the smaller that radius is,
yeah.
we would have to build more and more powerful accelerators to excite those particles because they're very heavy. And so that's why it's crucial. It's a nice formula you've derived, and I was just trying to see what we can learn from that.
Yeah, and I was going actually one step further when Clifford is saying the radius has to be very small. What I was trying to answer the question is, why does the radius actually have to be small? So, which is one of the recent developments in string theory that you can show, actually, you can determine the value of this radius, and you can show that this radius is actually small. So, yes?
World. And we did some experiments and found a particle that has mass in it. It's going to be massive particle. So straight out of that, we'll be able to infer what the radius of the
internal dimensions,
right?
yes.
So,
but
we're looking for a specific particle, right? So, if I take a 6-dimensional and I compactify 2 of those dimensions, 2 circles,
absolutely.
Are you looking for 2 particles?
No. Oh, well, the spectrum gets a little bit more complicated. You won't be looking directly for 2 particles. It gets a little bit more complicated. So we will need to discuss this. So it depends. So then it depends on the topology. It's not directly 2 particles. So you have 2 cycles there. So it's a little bit more complicated. So it depends on the topological numbers of the internal space. So it's not directly 2 particles. Or if you have got you can consider a 6-dimensional space. So internal spaces are determined by topological numbers, or so-called Betti numbers. And depending on this topological numbers, it's the spectrum of particles that you get in your four-dimensional world. Okay. All right. So let me go now one step further, which is the idea of trying to find a unified description of gravity and electromagnetism by applying the same concept instead of a scalar to a scalar particle, applying this to a metric. So my goal go ahead.
These extra dimensions, is it that the strings are living in all the dimensions and oscillations in that compactified dimension leads to heavier particles? Or is it that the strings can wander into these dimensions that pop out of like our three dimensions and move into another parallel three-dimensional world within that compact dimension? Or is it the string lives in all dimensions?
The string in principle lives in 10 dimensions. So it propagates in 10 dimensions, and later on, if you would like to describe our four-dimensional world, you will have to compactify those dimensions. But in principle, the string is moving in 10 dimensions from the very beginning.
So we ourselves are 10-dimensional objects, but the other dimensions...
It's later on when you would like to make contact with our four-dimensional world, when you have to say, okay, 4 of the dimensions are compactified. Okay? Yes?
At the string level, how are strings just packed together, or there is some kind of interaction between them? Is it that those interactions that make particles different, or what kind of interactions between the strings themselves?
It's the same thing. It's the same thing. What we basically are dealing here is when I will write down later on the action for the bosonic string, we are describing the free bosonic string. So we are describing a free theory. So there are no interactions between them. So it's not like in field theory where you have got different interactions. So, but what you can have is to describe, for example, with the bosonic string. So you've got something like this in field theory, but in string theory you will have a diagram like this, and you can compute a diagram like this by using the action. So you can compute then scattering amplitudes for string with an action that I will introduce later on for you when I describe the bosonic string. Okay? So you can have, again, the vertex operator formalism. I don't know. It will be a little bit too complicated to get into all this formalism of how to describe string scattering amplitudes. I think 4 lectures will be too much to try to address this question, but you can compute vertex operators and you can compute scattering amplitudes like you usually do in field theory. Okay?
Is there a specific reason why 6 of them are compacted in the end?
Yes. I mentioned that a moment ago when I said that for a superstring, if you are not living in 10 dimensions, what you get is states that have a negative norm, which are so-called ghosts, which doesn't make sense. So it's like you take the harmonic oscillator, you would like to compute the norm of a state, it comes out negative. It's a square that is negative. It doesn't make sense. You go to 10 dimensions and you see that these negative norm states are gone.
Should we, if you start assuming you have 10 dimensions, why is it that specifically 6 of them have contracted?
Because we live in 4.
Why do we live in 4?
That's a good question. That's okay. Well, yeah, you can. Well, that's what we see. The basic idea of physics is to explain what we see in nature. So
the only experimental input string theories.
So.
Another question.
Is it possible that because we are in a sense observing with detection of what is going on.
Yes.
That we only observe the 4 dimensions. But if our method of observation, our means of observation was any different when we observe more than 4.
Well, the basic idea is that you need to have a lot of energy in order to see the extra dimensions. So because they are so small, they are of the order of the Planck length, you need to have a very, very, very high energies to see this. So you need to have a very, very, very big particle accelerator in order to see these extra dimensions. It's like Clifford was saying a moment ago.
On Planck length, with the electromagnetic spectrum being our means of observation, then that's why we need to go to high energies in order for Planck's length to get to work. And so, if we're looking at now that is the case, then our observation is restricted to that. But I'm saying that another means of observation means that the 10D is observable in a different dimension. So I'm just projecting.
So you've just discovered a major topic of research called brain worms. This is exactly what people are trying. So people have begun to realize there's another, instead of just having everything curled up and small, maybe there's a reason that electromagnetic radiation, which is one of the things we use to look and see all those 4 dimensions, maybe there's a reason that only works in 4 dimensions. But some of the other forces, like gravity, maybe might work in the higher dimensions. There's a whole technology of things called brain worms, which you just essentially discovered.
It's amazing. It's amazing. There are many questions that you're asking that are topics of recent research.
That's fantastic. That's a really great question.
Yeah?
So actually, Joanne Hewitt, who's going to be flying in on the weekend, is going to give us some nice lectures about the phenomenology of extra dimensions. And I think she'll be mentioning some of that. So you'll hear more about that next week. That's a really good question.
Okay. Okay.
Sorry, I just want to know, is the reason you use 10 dimensions because you eliminate the ghosts? Is that the main reason?
Yeah.
Because could there be another dimension where you could also have elimination of these ghosts, say 46 dimensions?
Well, the problem is the supersymmetry only. You can only have supersymmetry. I think Professor Gates may explain this until 11 dimensions, so you cannot go to 44. So he may explain this in more detail from the supersymmetry algebra. So let me now go to where. So let me generalize this. Consider, so the goal is to consider to gravity and to unify gravity and electromagnetism. So here we've got, again, a nice exercise that you can do. So the basic idea dates back to 1919 when Kaluza, I think it was Kaluza, or was it Klein? It was Kaluza, who wrote a letter to Einstein saying, if I take the Einstein-Hilbert theorem that we considered yesterday, for general relativity in 5 dimensions instead of in 4, what I can see is I can derive in 4 dimensions an interaction, an action that describes gravity in 4 dimensions plus the electromagnetic interaction. And the way we can do this is in the following. So consider a metric. So the goal is to start with a 5D metric. plus 5D Einstein-Hilbert term. So that you don't get scared about the Einstein-Hilbert term, let me just write down a reference where you very easily can find it. And it's a very beautiful book. It's called Landau-Lifshitz. I think the spelling is this one, if I'm not mistaken. And it's called Field Theory. And there you will find many useful things that you actually need in order to describe these formulas of general relativity. You will find the definition of what a crystable symbol is. You will find the definition of a Riemann tensor, a Ricci tensor, and all the things, the Einstein-Hilbert action, all the things you need, you will find in this book there. And it's a very beautiful book. So
maybe a little easier than Landau-Lifshitz.
Yeah?
There's an article, it's on the web. It's by O'Rafferty. I wish I could spell that. It's called The Dawn of Gates Theory. It has a fantastic discussion of the Einstein-Hilbert term, specifically in the context of Kaluza-Klein theory.
Oh, maybe you would like to write down the reference because I...
No one knows how to spell it.
Oh, you don't know? Okay. I'm sorry. Okay.
The dawn of Gates theory. Yeah. Okay.
So let me start with a 5-dimensional metric, and let me start with the Einstein-Hilbert term in 5 dimensions. And what we can see is the following. I would like to restrict myself to states that are massless in 4 dimensions. So first of all, I would like to start with a metric, 5-dimensional metric. That looks in the following way. GAB. So I will use capital letters for 5D indices, 5D indices. And I will write this as G. I will define what G mu nu bar is in a moment. G mu nu are 4-dimensional indices. Then I will use G, the component, where I've got a 5 here, where we're sitting here. Then I will have a component where I've got a 5 and an index mu sitting here. And I will have a field that I call, well, let me call the G5 component. Let me just call it phi, which will be a scalar field. So basically, I've decomposed my 5-dimensional metric into a 4-dimensional metric, a metric that has a mixed component between 4 and 5 dimensions, and a metric that has a 5-5 component, where the most general thing I can write down is that G mu nu bar is equal to the 4-dimensional metric plus, on dimensional grounds, I need a kappa square here multiplied by a nu, where this is a 4-dimensional vector. Okay? And I basically can write down my 5, the component, G5 mu. I can write this as kappa multiplied by a mu. And as I say, this kappa is needed on dimensional grounds. So what we basically can now do is just to take the 5-dimensional Einstein-Hilbert action, and now you need to go either to Landau-Lifshitz or to the reference that, what was your name? Jeff?
Yeah.
That Jeff was referring to. So the reference that Jeff was referring to. And what you need to do is to plug in this definition of the metric there. And what we will see is the following. So we will, first of all, let me mention that we would like to restrict ourselves massless states. Massless states means I can eliminate all the derivatives with respect to d5. Which means when I see a derivative with respect to 5, which means d by dx5, I can set this equal to 0, because what we saw in a blackboard that I basically, I don't know where my blackboard is, but what we basically saw is that when I take the derivative, when I considered the Kaluza-Klein equation in 5 dimensions, what I saw is that when I take a derivative with respect to the 5 component, I get a mass for the 4-dimensional field. So what I would like to do is, in my formulas, I would like to set the derivative with respect to the x5 component equal to 0. So what we see then is that if I start with the Einstein-Hilbert action, so here comes an exercise for you, and this will be an exercise that is a little bit more difficult than the exercise Clifford was proposing a moment ago. But it will be a very good exercise, which is the following. So take the Einstein-Hilbert term in 5 dimensions. Let me call it L5. The action, the Lagrangian for the Einstein-Hilbert term. And look for me up what this definition of the Ricci tensor is. So, and what you see is that if you plug in this definition, you have to invert the metric that I wrote down here. So basically, you have to invert this matrix here. And you have to compute from me by using this metric here. And I will be asking you the answer to this question in the last lecture. So try to invert this metric for me using this metric. Please compute for me this Ricci scalar here, this Ricci tensor that we have got here. And what I would like to see is that once we insert this decomposed metric that we have got there, is that what we obtain is the following action. So after decomposing, and inserting d5 equal to 0, so don't take any derivatives with respect. So you will see that in the definition of this Ricci scalar here, you will see derivatives with respect to 5, the x5 component appearing. So please drop this derivatives. So what you will see is that you obtain an action that looks in the following way. I don't need the G4. Where this F mu nu is what Tony Z already told you. So it describes the field strength of electromagnetism. So we have got a d mu a nu minus d nu a mu, which is our F mu nu, which describes basically electromagnetism. In 4 dimensions. What we see from here, so this is the determinant of the 4-dimensional metric. So let me define my quantities here so that you can actually do the calculation. So G4 is the determinant of G mu nu of our four-dimensional metric. So we are basically dealing here with the square root of the determinant. I've got a minus sign here because of my conventions. I had a negative sign for the time component, which is why this minus sign appears there. And what I see here is the electromagnetic interaction in 4 dimensions coupled to the gravitational interaction. So basic conclusion is, by starting with a higher dimensional theory, what we see is that if we decompose our metric in this way here, what we see is that we are able to obtain in the lower dimensional theory a unification of gravity plus electromagnetism. Yes? G bar 5 is the G bar O. It's the determinant of this metric here. Let me just write this as G5. It's the determinant of this metric here. Put a 5 here. Okay? Yeah? Oh, thank you. Phi is equal to 1. For simplicity, thank you for asking. Just because I want to, phi equal to 1. It's a hard problem. Okay, so we can sit down in one of the afternoons and we do it together.
Great. Okay. So those of you who want to work on this problem, you find Melanie and Greece.
We will sit together and we can do it together.
It's important to get the general idea, which is purely Einstein-Hilbert, which is general relativity in 5 dimensions, gives you general relativity plus electromagnetism in 4 dimensions. But that step in the exercise is a hard one. So go ahead and assume it, and those of you who want to tackle it need some guidance from Melanie. Maybe she can.
But it's a very beautiful exercise. So it's something straightforward to do. You just look up the formulas. It's very straightforward to do. Just focus a little bit on the indices, and you will be able to do it. Okay, so, and basically, as I said, string theory is a higher order generalization to this formalism. So let me in the last couple of minutes start the discussion of giving you a reminder. So my goal is, even if I wanted to discuss today the complete bosonic string, and I didn't even start discussing the bosonic string, let me start by discussing in the last, since I've got 5 more minutes, what I can do is, in order to discuss the simplest string theory, which is the bosonic string, I would like to remind you how first quantization, so string theory is always formulated, quantized, so to say, in something that is called the first quantized formalism, which is the analog of the path integral formalism that we know from ordinary quantum mechanics. So people sometimes use string field theory, which is second quantization, but not many new exciting results have come out of string field theory, which is why people always use first quantization. So let me start discussing. So goal is to discuss the bosonic string. So in order to describe the bosonic string, let me give you a reminder on how we describe first quantization. So we will describe the bosonic string in something that is called first quantization. So let me give you a reminder of first quantization. Of point particles. So suppose in quantum mechanics, now you look, so the book I like a lot, I don't know whether you are very familiar with quantum mechanics, so the book that I like a lot is a book that is called BAME, so which I will be using next semester when I teach quantum mechanics. So if you would like to describe the propagation of a point particle, say in quantum mechanics from a point xi to a point xf, what you will do is to compute, in the classical theory, you will compute all the paths, so all different paths that go from a point, so xi at time ti to a point xf at time tf. So the goal is to describe okay, and what we basically do is to describe the motion of this particle in terms of what is called the world line. So the motion of the particle and the world line basically is a function x mu. Say we are describing the motion of a particle in 4 space-time dimensions. Tau is then our time parameter, and it will be mu are our 4 coordinates or 4 coordinates. And tau is a parameter that will be describing how at each point in time the particle will be moving. So we have got basically a function. I think I would like to restrict myself here just to three of the coordinates. So this function will be telling us how the particle will be moving as a function of time in our space. So at each point in time, we have a different point in our 3-dimensional space. So and this is what is called a world line. In classical mechanics, what we know is that the world line, that the particle will choose in order to move from a point xi at time tau I to a point xf at time tau f. The principle of least action tells us that the particle will choose the shortest path. So in a classical theory, the principle of least action will be telling us, I have to finish? Okay, I'm almost done here, because let me just finish here with the point particle, and I will be able to start with so in classical mechanics, we have got the principle of least action. Which tells us that the motion of the particle from one point to the other is the one that minimizes the action. So the particle will choose. I'm almost done here. I just have to finish the point particle. So particle will choose a path that minimizes the classical action. So we just go ahead and derive our action, which will be a functional of tau f, tau I, and we will have an integral from tau I to tau f multiplied by d tau, Lagrangian of x of tau, x dot of tau, and tau. So what we will see next time is how this action for a point-like particle looks like and how we can generalize this action to the motion of a string in 26. And the bosonic string will be moving. We will see that the bosonic string has to move in 26 space-time dimensions. So this is where I have to stop today. I didn't get as far as I wanted, but that's how far we can get.
Has anyone seen that before within the last week and a half? Where? Right. So I was hoping you were going to say the quantum mechanics course that Douglas Smith gave you with. So this will be a second time to see it, refresh your memory, and then so start looking back on your old notes.